So the alveoli are the units, the structural units that make up the exchange surface of the lung. Exchange meaning how oxygen is transported across that thin membrane. And we get to the alveoli first in what's called a respiratory bronchiole. A respiratory bronchiole is a bronchiole that does not have any collagen on it. It's not made of any collagen, and it's called respiratory because in place of collagen, it now begins to have a few alveoli which balloon off of it. It's just these little pouches that constitute the exchange surface of the lung. Respiratory bronchiole will branch into, I don't know, maybe 2, 3, at most half a dozen alveolar ducts. An alveolar duct is now no longer a bronchiole because there's not really much integrity to the tube any longer. In fact, it's just a collection of alveoli that form a kind of a duct. I think of it a little bit like the road leading into a cul-de-sac. The cul-de-sac is at the end of the alveolar duct. We call this an alveolar sac. So you can see some examples of that on the board up there. An alveolar sac is just the end of an alveolar duct that, much again like a cul-de-sac, is just a collection of the alveoli at the end, at the terminus. All right. This is where gas exchange happens, from respiratory bronchiole to alveolar duct down to alveolar sac in any of these alveoli. Alveolus is the singular of that. All right, so let's look at a little bit more detail here in this cartoon. There are two types of what are called Numa Sites. Numa Sites being essentially the lung cells, the cells that make up the surface of the lung. Pneumocyte type 1 is a simple squamous epithelial cell. Simple meaning a single layer, squamous meaning squashed down and very thin. So the purpose of that is so that the gases that need to be exchanged, either carbon dioxide or oxygen, don't have very far to travel to get from the outside to the blood or vice versa. So a simple squamous layer of epithelial cells. The other type of cell is pneumocyte type 2. These are called septal cells. A septum is simply a wall, and in this case, septum referring to the walls between adjacent alveoli. These septal cells live in those regions in the septa between adjacent alveoli, and their primary function is the production of a surfactant. Now, a surfactant is some kind of oily secretion. It has several components in it, the primary function of which is to reduce surface tension. Now, we all know that water has a high surface tension because of the intermolecular bonds between the water molecules. And because of that, water beads, right? If you put a drop of water on the back of your hand, you'll notice that it beads up. And why might you not want water beading up on the surface of the alveolus? Anybody think about that? Well, I'll just, if no one wants to venture, it's essentially because the air that is exchanging, the gases that are exchanging, want to be as close to where they're going as possible. And if they have to diffuse through a huge bubble of water, then that's going to significantly reduce the efficiency of that gas exchange. So you have a surfactant which allows the surface of the pneumocytes, of the epithelia, to remain moist because that's what they need. They need to stay the tissue needs to stay hydrated. However, it prevents a large surface tension bubble of water to build up on that surface. So there's a number of things that are in this surfactant, different phospholipids and proteins. The specific phospholipid is DPPC, dipalmitoyl phosphatidylcholine. Say that fast 10 times. All right, and then you can notice in and around the junctions of these alveoli are these capillaries, and there are endothelial capillary cells that invest this structure. The other thing to point out, the other type of cell that you'll see here is these so-called dust cells. They're macrophages that are specific to the lungs, these alveolar macrophages. We call them dust cells because there are all kinds of inspired or inhaled smudge in the world, and dust of all kinds of sorts. And so these macrophages, their job, if that dust is not caught up in the mucus elevator, the mucociliary escalator, or whatever I was calling it, then it's the job of these macrophages to find and remove that junk. All right, so let's look even closer here. So on the left, we see a respiratory bronchiole leading into an alveolar duct and terminating in an alveolar sac. And we're going to look very close at the lining of one of these alveoli. And what we see is we have in the alveolar airspace a surfactant on the surface of the simple squamous epithelium, that is the alveolar epithelium, that has a fused basement membrane, which is fused to the capillary endothelium, a single layer of squamous epithelium that forms the capillary that surrounds the alveoli. And we can see a red blood cell there. So that surface, the boundary between what is ostensibly air, the outside world, and your blood is less than half a micrometer. That's about 2/100,000ths of an inch. It's hard to wrap your mind around how thin that is, but it's incredibly small. It's incredibly small. A red blood cell, a single red blood cell, is about 7 micrometers, and so this is a 14th, less than a 14th or a 15th of the width of a single red blood cell. Very, very, very delicate, thin membrane, which is, I'll show some pictures later on Friday, I guess, of some lung cancer and emphysema caused by smoking to show you how easily damaged this very delicate surface is. But also the point here is to show you how short a distance that gas actually has to pass for it to enter the bloodstream, or gas to come out of the bloodstream into the air. All right. So here are the key steps in respiration. The word respiration can refer to two things. There is external respiration and there is internal respiration. What we're going to talk about today is, or the rest of this unit, is external respiration. I'll talk a little bit about internal respiration when I get to the GI chapter. External respiration has basically 3 processes to it. There's pulmonary ventilation. This is simply the process of moving air to and from the exchange surfaces in the lungs. This is what we think of as breathing, right? They're just inhaling and exhaling. That's pulmonary ventilation. Then once we have gotten the air to that exchange surface, there needs to be gas diffusion going in both directions. And then finally, the cardiovascular system takes over for transport, oxygen transport from the lungs to the peripheral tissues, and conversely, the transport of carbon dioxide from those peripheral tissues to the exchange surface of the lungs where it's exhaled. Then internal respiration is simply what the cells in the periphery do with that oxygen once they have it and how they turn it over into carbon dioxide. We'll talk about that a little bit later. Most of you probably had most of those details already. Okay, so just a few definitions so that you have them. The concept here being that abnormal external respiration is indeed dangerous. So hypoxia is the condition where you have low tissue oxygen levels. Hypo meaning low, oxia, low oxygen levels in the tissues. Anoxia is a complete lack of oxygen. And if there is anoxia, tissue dies. Apnea is the word, A-P-N-E-A. Apnea is the word that we use for a temporary cessation of breathing. Okay, so this happens during sleep. Maybe some of you know someone with apnea. Maybe one of you has it. Some of you have it. It's often associated with snoring. But people with apnea, you will, it's the kind of thing where it's like, where they just sort of stop breathing for a while and then the body does it again like that. I had to close my eyes to get myself in the roll there. All right. So nothing too intense here, but just remind yourself from high school chemistry about Boyle's law. And so this is all towards reminding you of the fundamental basic physics behind, or was it chemistry or physics that you talked about Boyle's law in? Maybe. Chem, yeah, I guess so. But the idea that pressure is inversely correlated to volume. So just to remember that, you have here Han and Luke and Leia, the crew, in the trash compactor, and the volume is going down on them, and the pressure is going up on them. So as you make the volume smaller, there's more interactions with the wall of the container. And then oppositely, we have Luke in a big wide open space, feeling sort of at peace as he watches his dual sunset. Beautiful. Okay. Inversely related. So what does this have to do with any of this? As you inhale, inspiration, we're going to increase the volume of the lungs. By increasing the volume of the lungs, we're decreasing the pressure in the lungs relative to the outside world, and that the air from the outside, the higher pressure of the atmosphere, will push air into the lungs, all right, to normalize that pressure difference. Oppositely, when you exhale, when you expire, you are decreasing the volume in the lungs, and by so doing, you're increasing that pressure transiently so that the pressure difference between your lungs and the outside world will force the air out of your lungs. All right, so that's all that it's about, is just changing the volume of the mediastinal compartment where the lungs reside. And by changing the volume, we're changing the pressure, allowing air to come in and out. I'm showing a little, one of my little yoga pictures over here to have you understand that it's not just the thoracic diaphragm that is changing that volume, but also that it involves changes and support, changes in the volume of the abdomen through the pelvic diaphragm and the posterior and anterior walls of the abdomen, etc. All right. So let's look at, that's ventilation. Now let's look at the exchange process in external respiration. Here we have this figure we've seen before with the circulatory system. And we're going to zoom in just on a single alveoli, or an alveolus, in the lung, and that tiny 0.5 micron respiratory membrane. Well, blood that is returning from the system is deoxygenated blood. It's being sent to the lungs from the right side of the heart. The partial pressure of oxygen in this blood is about 40 torr, 40 millimeters of mercury, whereas the partial pressure of carbon dioxide is approximately 45 millimeters of mercury. It turns out that the partial pressure of these two gases in the atmosphere, so the atmosphere is what? Is it 760 torr? Is the pressure of atmospheric pressure. Of that 760, 100 millimeters of mercury is 100 torr is the partial pressure of oxygen, whereas the partial pressure of carbon dioxide is about 40 torr. Although that number is going up. So what we see here is that oxygen is going to flow down its concentration gradient. It's going to diffuse from the alveolus across the membrane into the blood, all right? Because the blood is an area of low oxygen concentration, and the air in the alveolus is relatively high, and vice versa. The carbon dioxide has a higher partial pressure in the blood than it does in the air. So, for example, that's kind of like like you open a can of bubble water or something like that, soda water, and the carbon dioxide bubbles. The carbon dioxide concentration in the soda water is higher than the atmospheric pressure, and it's going to come out of that and go towards an area of lower concentration. Does that make sense? Yeah. All right. Then on the other hand, the cardiovascular system sends that blood back to the heart, and it gets pumped out to the rest of the system. And when it's in the periphery, the partial pressure of oxygen is still around atmospheric pressure at about 95 torr, whereas the concentration of oxygen in the peripheral tissues is about 40 if you're sitting there as you are currently. If you were sprinting, it would be lower, but it's about 40 here, and the oxygen diffuses out of the blood into the peripheral tissue. Again, the concentration of carbon dioxide is 40 in blood returning to the peripheral tissues from the left side of the heart, and the carbon dioxide in the peripheral tissues is about 45. So we get the opposite exchange as to what we would see in the lungs. Does that make sense? Pretty straightforward. Okay. So this brings me to hemoglobin saturation. This is certainly the most challenging part of respiration, is understanding hemoglobin. Hemoglobin is the carrier molecule for this oxygen, and even carbon dioxide. It can carry some carbon dioxide. So I'm going to talk at length today, the rest of today, and probably half the time on Friday, about how hemoglobin actually works. First of all, hemoglobin is a tetrameric protein, meaning that it has a quaternary structure. It has 4 subunits, 2 alpha chains and 2 beta chains that associate with one another. This is the protein that is packed inside of a red blood cell. A red blood cell is pretty much just a stripped down cellular container for hemoglobin. There's not much else in a red blood cell. There's no nucleus, there's no mitochondria, they're not really metabolically active. They're just packed with these hemoglobin molecules into a container that's this shape that tries to maximize surface area to volume. So again, oxygen, a gas, can maximally diffuse across that surface and get into the cell so that it can bind to hemoglobin. What is it specifically in hemoglobin that binds the oxygen? Well, it is this structure called the heme molecule. The heme molecule is made up of two parts. It is, first of all, a porphyrin ring, and which is all of those chemical bonds that you see on the left there. And embedded in the middle of the porphyrin ring is the iron in the +2 oxidation state. So the iron and the porphyrin ring together are the heme molecule. We all know that iron binds oxygen. So, for example, here is this piece of art by this guy, Julian Voss-André, that over the course of several years turned rusty. He left this piece of steel, this iron sculpture out with the iron embedded in the middle of it to show you that indeed oxygen binds to iron. All right, so let's continue to look at this. So in the left-hand side, we see the heme molecule coordinated to one of the histidines in a globulin subunit, in an alpha subunit of the hemoglobin. The histidine coordinates to the iron, holds that porphyrin ring in place. In the deoxy case, when the iron is not coordinating the oxygen molecule, that flat surface of the porphyrin ring, which is a highly conjugated system there for those of you talking about that in organic, it actually displaces the porphyrin ring by a very small amount, only 0.4 of an angstrom. That's a really small amount, but it acts as a molecular trigger, and we'll see how that molecular trigger works in a bit. That 0.4 of an angstrom compared to when oxygen is actually bound to the iron. So when oxygen is bound to the iron, it gets resonance stabilized. So Fe2+ will bind to O2, but it can shift between oxidation states with the iron. One of the electrons in the d orbitals of the iron 2+ can shift itself, resonance stabilize itself, and form what's called the superoxide ion. Oxygen is, of course, quite electronegative, and those two oxygens over there can happily hold on to that extra electron for the iron. It gets resonance stabilized. This change in the oxidation state, this resonance between the two oxidation states for the iron, is what changes the diameter of the atomic radius of the iron and allows it to pop up into the plane of the porphyrin ring a little bit better. It condenses that shell by the removal of one of the electrons from that d orbital. And there's also a mass effect that by the oxygen that helps pull it up. So that's all the origin of the 0.4 of an angstrom displacement there. Probably more biochemistry than most of you want, but it's interesting. All right. So what effect does this binding of oxygen have? This is a good opportunity for us to introduce the concept of allosteria. So when oxygen binds to the hemoglobin, we get this slight molecular shift. This leads to a 15-degree change in the rotational axis or orientation of the hemoglobin subunits along the axis of the molecule. This rotation in oxy versus deoxy hemoglobin is going to change the ability of this effector molecule, specifically oxygen, to bind at other sites in the molecule. So once hemoglobin, the hemoglobin tetramer, binds oxygen at one site, it will affect the relative ability of oxygen to bind at other sites in the molecule, right? Because we're slowly shifting that hemoglobin. As it shifts its global structure, it's going to change subtly change the architecture of the entire molecule, but that is translated into the porphyrin rings of the other sites that are not bound, and it's going to change the affinity of those sites to bind oxygen. Is that making sense? Probably. Who's talked about hemoglobin before? Who's had this in their class? Only a couple of you. All right. Well, you may go deeper than you've seen, or maybe not. So here are a couple GIFs. If I didn't explicitly say it, let me read it to you. Allosteria is the alteration of the activity of a protein through the binding of an effector molecule at a specific site. That's a general concept. So a lot of different proteins can be allosteric. You can have the binding of an effector molecule that's going to change the binding of a subsequent molecule to that protein, either help it or hinder it. If, as in the case of hemoglobin, it is a helping, then we call this cooperativity. So the word cooperativity simply, in terms of hemoglobin, means that hemoglobin can transmit some sort of intramolecular information about whether the binding state of oxygen, whether oxygen is bound to another site elsewhere in the molecule. So because there are 4 subunits, you can see here that here's one porphyrin ring, a second, a third, and a fourth. One hemoglobin molecule can transmit 4 oxygens. The binding of one oxygen to one site is going to affect the cooperatively affect the binding of oxygen at other sites. So the more oxygen is bound to hemoglobin, the easier it becomes to bind oxygen, is what I'm trying to tell you. And we'll see the implications of this in a bit. This is just sort of showing you the molecular conformational shifts that happen with the binding and unbinding of oxygen there. All right. So this is probably the most important slide to understand in this set of slides. And this is the hemoglobin saturation curve. I'm gonna sit on this slide for a little while until I feel like we've gone through it well. So along the x-axis, we have the partial pressure of oxygen that a hemoglobin might find itself in, all right? And then along the y-axis, we have percent saturation. So what we're looking at here is for an ensemble. This is for an ensemble of hemoglobin in whole blood. This is not a single hemoglobin molecule, all right? This is for an ensemble of hemoglobin. And given a billion hemoglobin molecules, what's the percent of sites in all of those hemoglobin that will be bound to oxygen at a given partial pressure of oxygen? Does that make sense? All right, like what we're actually looking at, and I'll explain why the curve looks like it does in a bit. But it's essentially a result of allosteria. So let's point out a couple partial pressures here. First is the partial pressure of oxygen at the lungs. And so this is not percent, it is torr, millimeters of mercury. 100, you'll remember, is the number I said was the partial pressure of oxygen in the atmosphere that we're breathing. More or less, depends on elevation. And at this point, the saturation rate for hemoglobin is essentially 100%. So when hemoglobin finds itself at 100 torr, the affinity for oxygen is pretty much maxed out. Hemoglobin is anything above about 100 torr. Hemoglobin will have essentially all of its sites occupied by oxygen. And you can see on the left here how I'm representing that. Both the alpha and the beta sites are all occupied there. Now, another pressure to point out is right here at about 40 millimeters of mercury. And this is the pressure, you'll remember, of the partial pressure of oxygen that you'll find at the peripheral tissues, maybe at your muscle cells or your adipose cells or your brain cells, wherever it is that the oxygen is being delivered. So at this concentration of oxygen, we have about a 75% saturation rate. So in general, moving from the arteries, moving from the lungs to the peripheral tissue, your hemoglobin is delivering about 25% of the oxygen that it's carrying. Does that make sense to you? Why? Why not unload it all? What do you think? What makes sense about that? How come? Why shouldn't we? We're like schlepping 3/4 of this oxygen back and forth all the time, and it's not being delivered at all. What do you guys think?
When it's already saturated. Does it make it more?
There is an efficiency element to this that we're going to reveal. I haven't given you all the parts. I'm trying to let you climb through it. There is an efficiency part. You're right about that, but that's not the exact rationale behind the thing that I'm pointing out right now. So we're at rest. We're not running a race. We're just chilling out in class, trying to deal with the professor, and there is still 3/4 of the oxygen sitting on your hemoglobin at all points in time. Well, yes.
Would that be in a certain need that?
It's an oxygen reserve. So you guys are sitting here holding your breaths, waiting for me to give you the answer, right? You're sitting here waiting, holding the breath. And as you do that, maybe your peripheral tissue, maybe that partial pressure is going down a little bit because we're not supplying a regular source of oxygen. You'll notice at this point, the way this curve is set up. So before that, it's about this kind of, it's not too far from a gentle slope on that curve. Okay, pretty much more or less kind of linear, gentle slope. After this point, that slope, the slope of that curve changes dramatically, doesn't it? So for a very small shift, so this is where we normally are. This is where your cells normally are. But if anything perturbs that, maybe your professor makes you hold your breath. Maybe a werewolf senator from hell comes in the door and you got to run. You got to hide. Physical exertion. The partial pressure of your tissue, the oxygen in your tissue begins to go down because you're consuming that oxygen. You want to be able to deliver that oxygen more rapidly, right? This is an oxygen reserve. You're keeping 3/4 of the oxygen that your hemoglobin can hold in reserve as a buffer towards problems. Maybe you take a face dive, God forbid, into a cold river. You're like out there ice fishing and you fall through the ice, splash. and you're under the water for a few minutes and trying to get out. You have that oxygen in reserve. Sometimes your body needs it. All right. Yeah, I think that's all I'm going to say on this slide. So I guess you could see this here. If we look at these 4 panels, the change between 100% saturation and 75% saturation is 60 torr. It's a profound shift in partial pressure of oxygen. Whereas the shift from 75 to 50, that's only 12. It's only 12, right? And then here, it's only 10. If you're getting down here, you're really in trouble for sure. Okay. So you following the rationale here behind the shape of the saturation curve? The shape of the saturation curve is a result of the allosteria. It's a result of the allosteria. All right. So when you are in the presence of oxygen, you're going to be able to bind oxygen more readily. And when you're not in the presence of oxygen, you're going to be able to unload oxygen more readily. Okay? So hemoglobin is tuned to be able to do 2 jobs. It's going to be tuned so that when it's around oxygen, it will bind it very easily. And when it's not around oxygen, it will unload it very easily. We're going to unpack that a little bit more here. I'll say this. Hemoglobin, in graduate school, I was at Notre Dame, there was a course in kinetics, advanced graduate level biochemistry kinetics. And we spent like 2/3 of the semester talking about hemoglobin. Hemoglobin is far more sophisticated than even I'm going to be able to talk about with you here today. But I'm gonna show you. I'm gonna like pull the curtain back just a little bit for you, so you can see a little bit of how it works. So this is what I've been alluding to, right? Here's the curve. At rest, when you look at the change in oxygen delivery between the lungs and the tissue, when you're at rest, that's about 21%. I had 25 in the last slide, something like that, in the 20s, percent of oxygen delivery between what the complete capacity of the hemoglobin is. However, say you start exercising or running away from werewolves or whatever, the partial pressure of oxygen in the peripheral tissues, that oxygen demand of those tissues is going to reduce that level, maybe as low as 20 millimeters of mercury. You're running, you're at your anaerobic threshold. You're at the maximal point of oxygen consumption by the cells, all right? And we move into a different part of the curve, and with just that small shift in the partial pressure of oxygen, we're able to deliver an additional 45% of the oxygen that is now held in reserve on that hemoglobin. So we're able to go from 21% delivery to upwards of 2/3, upwards of 66% of the oxygen that our hemoglobin has the capacity to carry. All right. So let's take a small step into the kinetics that's behind this. And it's important to understand that there are 2 states for hemoglobin. There is the T state and the R state. T for tense, R for relaxed. The people who have talked about hemoglobin in classes before, have they gone here? Yes, you have. Okay. And the T state definitely has a lower affinity for oxygen than the R state. The R state is relaxed, it's able to bind oxygen, no problem. The T state is where the porphyrin ring is more tense, less flexible, and less able to bind oxygen than the R state. Now, there are a couple different models. In fact, there's about 5 models out there. I put 2 of the most popular models on the screen. And in fact, probably the one that's closest to being correct is the model that's somehow a blend of these 2 models, somewhere in between these 2. These models, for how this all works, are the 2 that I'm going to show you are the concerted model and the sequential model. So concerted is a model where all of the hemoglobin monomers, all of the monomers are all in the same state at once. The molecule is doesn't go through a gradual shift. It's all in one state or another state. So, for example, when it's in the T state, it doesn't like to bind oxygen. When the hemoglobin finds itself in a low oxygen situation, the T state is heavily favored. It can be in the R state. There is a small, in the concerted model, there's a small number that are in the R state. No pun intended. But most of them are in the T state. Whereas when you are in the presence of lots of oxygen, the oxygen is going to bind, but the R state is strongly favored. So there's this concerted, coordinated conformation of each of the subunits. All right. Whereas in the sequential model of cooperativity, we have, as the name would lead you to believe, there are sequential changes that happen to one subunit and then the next. So, for example, when you don't have much oxygen, the equilibrium constant is strongly favoring the T state, which will boot that oxygen off. But if you do have one on, it will subtly affect the conformation of adjacent subunits, but the one that is catty corner is still in the T state. And then if you increase the CO2 level or the oxygen level, we have this sort of gradual change, this sequential model of cooperativity. So that in this model, you have several different states. You have both R and T state and some kind of transitional state, all in the same molecule. What's probably going on is actually neither of these. It's probably some sort of gradient where all of the monomers are in the same conformation, but it's a gradient between 2 extremes of all R or all T. All right. So those are the models of how these binding states work. All right. So let's look at the consequences this has on the binding curve. So if you had all T state, this would be the way the binding curve looks. Essentially linear. For the range of oxygen that we're talking about. I mean, it's not actually explicitly linear, but it looks linear to us because of the scale. And the point here is that if you could somehow stick the molecule in T, if there wasn't the chance to go to R, there was no allosteria. If it was permanently stuck in T, this is what the binding state would look like. So at 100 millimeters of mercury of oxygen, we'd only have about maybe 20-some% of the binding sites would actually be bound to oxygen. oxygen does not want to bind to it when it's in the T state. If it were stuck permanently in the R state and was not able to be in the T state, we would see this blue curve. We would see the blue curve, all right? So at, you can reach this same, 20-some percent that we get at 100, you reach that at just a few millimeters of mercury of oxygen. So really highly favored. So when it's in the R state, it wants to bind oxygen. All right. Indeed, the curve that we see is somehow a blend between them. It's a blend between the R state and the T state. Next time, I'm going to keep talking for a couple minutes, but next time, the bulk of the next lecture is going to be looking at ways that either the T state or the R state can be more or less favored to slightly shift this purple curve to look more like the blue or more like the red. Look more like the red state, the R state, or more like the T state. All right. Shifts in that observed binding curve are going to lead to all kind of physiologically relevant, important phenomenon that we're going to be talking about. You guys following this R state, T state thing? Okay. Good. Yeah, this story is great. I love this story. 2,3-bisphosphoglycerate is this fun molecule right here. I don't know how many of you have dug deeply into glycolysis, but for those of you who have, you will perhaps recognize this molecule. It is a side path in glycolysis, and we'll look at that side path. I'll show it to you. But it's an interesting molecule. It's made, so where does glycolysis happen? Glycolysis happens in peripheral tissues that are going through internal respiration, meaning they're using oxygen to oxidize the carbon in glucose to produce ATP. They break glucose down to pyruvate, which goes into the mitochondria, and we get ATP out of it. The carbon byproduct being carbon dioxide. All right. So 2,3-bisphosphoglycerate is a metabolic marker, and we'll see exactly what it marks in a moment. But what it does is stabilizes the T state. So if you look at pure hemoglobin from the blood that has no 2,3-bisphosphoglycerate, the curve looks more like the red curve. If there is the presence of 2,3-bisphosphoglycerate, it slides the curve this way. All right, so that if you look at the partial pressure of oxygen at the tissue, when you are heavily exercising, in the presence of 2,3-bisphosphoglycerate, this is what's giving us this 66% of oxygen. It's actually due to the presence of this molecule. If it's not there, the curve shifts that way, and we get a more R state delivery. Only 8% of the oxygen would be delivered at that 20 millimeters of mercury. All right. So I'm going to pick up here next time. I don't have time to dive into this one. But this is where we'll pick up next time.